Hello there, and welcome to this video on sequences. We are starting a new unit called Infinite Series, and our first thing is a little introduction into some sequences, something you've probably heard of before and have seen in prior classes. So you can see our objective for there, and you see these three things down here. Excuse the bell. Differential calculus, a lot we did last year. I mean, we're constantly using derivatives, but we studied it for the most part, the first part of Calc AB. Integral calculus, we just finished a bunch of integration techniques, but we studied that as well last year. And then here is our next little topic, infinite series, we're going to be working with moving forward. So we're going to start with something that I know that we've talked about, and that's Zenos Paradox. When Zeno talked about someone walking towards a wall that is a determined distance, we'll say a meter, and if we continue to cut the distance between the person and the wall in half, we would never actually reach that wall. However, it is a definite distance from the wall, the person. So if we write those distances from the wall, we can write them as a sequence. So we can write it as 1/2, and then 1/4, and then 1/8, and then 1/16, etc. And what we can do is with these terms in the sequence, we can come up with a formula that will give us the nth term. This is the first term. This would be the second term. This is the first term. This is the second term, third, fourth, and we can go dot, 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 all the way to the nth term. So if we wanted to know what the 20th term of the sequence would be, we'd be able to figure that out. And the formula, you might be able to figure it out. You can think about it. Look what's happening to the denominator here, as what's the numerator stays the same. You can see that this is actually what that is. You can see it right there. And as we plug in different integer values for, well, we start at 0, because if you plug in 0, you get 1. So this actually, if you wanted to start this, is really 1, then 1/2, 1/4, 1/8, etc. Formally, a sequence is an ordered collection of numbers defined by a function f of n on a set of integers. So your n's are going to be integers. The values a sub n equal f of n are called the terms of the sequence, and n is called the index. So informally, we think of the sequence as a list of terms. So here is one way to do it, or you just saw in the previous example, 0, 1/2, 1/4, etc. The sequence does not have to start at n equal 1, but may start at any value, 0, 2, or any other integer. When a given formula, that's what we just talked about, it's called that general term. So that 1/2 to the n is that general term, because it's given by a formula. So here are some examples of sequences, different sequences. You're going to see we're going to have the general term, we're going to have the domain, and then the actual, some of the things of the sequence. So what I'm going to do is I'm going to do the first one. So here's the general term of the sequence, 1 minus 1 over n, when n is greater than or equal to 1. So what we're doing is putting in n equal to 1, then 2, then 3, then 4 into this sequence, and we're getting these results. Look at the next one. Another sequence general term, -1 to the n times n, when n is greater than or equal to 0. And if you notice here, what does that -1 to the n do? It alternates those signs. You can see that every other one is going to be negative. Here's another general term of a sequence. You're going to see we're going to revisit this sequence a little later. This has some applications to it. So we have you can see it, and for n is greater than or equal to 3, and then here are the numbers that determine the value of that sequence there. Again, at any time of the video, you can pause, stop the video, and kind of copy down whatever you need to copy down, etc. You'll see if you follow along in the book, I'm kind of explaining some of the readings in the book, if you wanted to do that as well. So what does it mean to be recursive? If you're a programmer, and I know some of you may be programmers, you may have learned some things, recursiveness in programming, but what does it mean? What does it mean to be recursive? If you think about it, the first term is given, the nth term, a sub n, is computed in terms of the preceding term, a sub n minus 1. So if you look at this first recursive sequence, here's a sub 1, And here is the nth term of that sequence. And what we do is if we're going to find, it asks us to compute a sub 2. So if we're going to plug a sub 2, we're going to find 1/2. We're going to plug 1 in here. I'm sorry, 2 in here for n. 2 minus 1, so that becomes a sub 1 plus 2 over a sub 1, which is equal to 1/2. 1 plus 2 over 1, which is equal to 3/2. Now the recursiveness comes in when we find a sub 3. Again, now we're putting 3 in there, which means it's going to be a sub 2 plus 2 over a sub 2. And we're going to use it again. So it's going to be 1/2 times 3/2 plus 2 over 3/2. And that is going to give us a value of 17 over 12. And then if we found the fourth term of the sequence, again, the recursiveness of it gives us something like this, which is going to give you and I know you're following along very quickly with the math. And that gives you 577 over 408. Now take a moment, and what I would like you to do is find the decimal approximation for these three fractions. I'll do the hard one for you. I want you to do it for 17/12. Pause the video and see if you cannot make some conclusion about that. Well, if you did, you should see that these values are actually approaching 1.414. Actually, this one is 1.414216. So as we get higher up in this sequence, it is approaching. Anyone know what 1.414 is? I'm sure a lot of you know. The square root of 2. So yes, this is actually, this sequence is the approximation of the square root of 2 produced by Newton's method. And we'll talk about that another time. Limits. Oh, we're not getting away from limits. We started Calc AB with limits, and we're back here in BC with limits again, the limit of a sequence. And I'll let you read that. And just, I want to highlight two of the bullets down here. If no limit exists, we say it diverges. Just kind of like when we did improper integrals. Remember the improper integral, when we found that limit, it didn't exist, it diverged. So if you look at here, what's kind of happening here as the terms of the sequence continue, it approaches a limit. So let's consider these two sequences here. We want to maybe evaluate the limit of these sequences and see what's kind of going on. So let's take the limit of this guy as n goes to infinity. We want to see as these integers, remember, so this is going to start at 0 or 1. We'll start at 0, so we get 4 over 1. Then we plug 1, we get 5 over 2. Then we plug 3, we get 7 over 4, on and on and on. But knowing your properties of limits and evaluating limits, you probably have already recognized that this limit is equal to 1. So if we look at the other one, take that limit of cosine of n. Again, because of your expertise with limits, you should recognize that regardless if we put cosine 1, 2, 3, 4, 5, what is happening with cosine? Yeah, absolutely. It oscillates back and forth, goes up and down, and you'll see that really this limit does not exist as it goes to infinity. And there's a couple pictures. Here we go. Here's one. Look at that, approaching 1. And then here's the one that's cosine all over the place as we put in those integers n. So keep that in mind. Here are two facts about sequences. The limit does not change if we drop finitely many terms of the sequence. Because you think about it, when we take in the limit, we're going to infinity. So if we drop the first 3 or 4 or 10, it's not going to make much of a difference. If c is a constant and a sub n is equal to c, then for all n sufficiently large, then the limit is just going to be that constant. So keep that in mind. Remember, it's just a constant. So many of the sequences we're going to be working with can be defined as functions. So remember, with the n's, we're only dealing with integers, 1, 2, 3. But when we turn it into a function, we're going to be dealing with all values, all numbers. So here's a sequence defined by a function. So if we look at this, we can see that the limit of the sequence equals the limit of the function. So we want to find the limit of the sequence. Find the limit of the sequence. Well, let's write an nth term first. I'm hoping you're able to, again, pause it and try to come up with the nth term before moving forward. I'm just going to kind of keep going along. N squared, so it's 2, 3, 4, 5, excuse the bell, over 2, because you see that stays constant with each member or each term of that sequence, all over n squared again. Now if we turn that into a function, we can say that the limit using that theorem of a sub n as n goes to infinity is equal to the limit as x goes to infinity of x squared minus 2 over x squared. And again, knowing you know how to evaluate limits, you would evaluate that limit to be 1. All right. Here's another example for you. So as it's going to infinity, we're looking at this. So, but before we do this, you might notice, okay, we get infinity plus natural log of infinity over infinity squared. We're going to get an infinity over infinity. What rule can we use when we get an infinity over infinity form? If you said L'Hopital's, you would be correct. It is L'Hopital's rule, but we can only apply L'Hopital's rule to functions. So what we're going to do is we're going to rewrite this as a function. And the mathematics here is important. It has to be continuous here for that to happen. Again, if we're talking about integers here, we're going to have that kind of that stat plot that you saw back here. And we want a continuous function in order to take derivatives of things. We need to be continuous. So we take the derivative here using L'Hopital's rule, L'Hopital, and you're going to get 1 plus 1 over x over 2x. If we evaluate that limit now, look what's happening here. 1 over something getting very large is going to 0. So you're going to get 1 over something getting very large. It's going to go to 0. That sequence is going to converge. So here's an application of something called Balmer wavelengths. And it plays an important role in physics and chemistry because it determines the ionization energy of the hydrogen atom. So if you looked in your textbook, you would see a table of values for n being greater than 3 and moving up. Here I have the limit written. As you notice, I actually kind of mess something up here. There should be an x here because I'm turning it into a function. And when you evaluate this limit, you see the degrees of the numerator and the denominator, and you would find that the limit as it goes to infinity is 364.5. That is one of the sequences we saw early on when we were doing that, or similar to this. And what I have down here is just a little talking about the visible spectrum here and the wavelengths of what's kind of going on there. You can see that 364.5 is going to be down here somewhere, ultraviolet light. So it's a little, some of you probably know more about light and stuff from your physics experience. So, but a little application of that why we would take a limit and where that would be. So this is just a quick little introduction to sequences. And you know, there's some more reading you can do in your textbook if you like. This was your homework, which you knew about. I told you about this in class. So please attempt to do some of those problems. We will entertain some questions on Wednesday as we begin before we move on with sequences. Okay? So I hope you enjoyed this, and Johnstone out.